Okay, hey guys, this is Bunny Tyagi, and today we're going to do one of my recent favorite questions that we encountered in the lunchtime. And this question is checkpoints. So let's start. We are given with endpoints on a 2D Cartesian coordinate system, the ith coordinate being xi, yi, and along with these endpoints, we're also given a fixed integer c. And we may perform operations on one or more points such that if before an operation the coordinate and the abscissa is xi, yi, then we can move it to xi plus c, yi plus c, or xi minus c, yi minus c. We can apply this operation, this one move that we are calling it one move, multiple times on one point itself, also on several points too. So our objective right now in this question is we have to decide the minimum number of checkpoints that we're going to need such that it's possible for me to make several moves on different points, such that after I've made all of those moves, each and every point must belong to some or the other decided checkpoint. And so I have to decide on the minimum number of checkpoints that I'm going to need. After I've decided the minimum number of checkpoints that I'm going to need, I'm going to have to place those checkpoints on the places such that the moves that I have to do in order for me to send the entire points to their respective checkpoints, those number of moves are minimized. So our primary objective is to minimize the number of checkpoints first, and after we have decided on the minimum number of checkpoints, we're gonna have to decide how to place those checkpoints such that the number of moves that I have to do are also minimized. So let's start with the input. We're gonna be given t, which denotes the number of test cases, and then we're gonna given two integers n and c, n being the number of points that we're gonna be given, and c the amount by which we can displace that point by plus c or minus c to both the ordinate and the abscissa. And then n lines follow xi, yi. So let's see this example input that we're given. So the number of test cases is 1, the n value is 3, and the c value is 1. That means if I am given a point xi, yi, I can in one move I can shift it to xi plus 1, yi plus 1, or xi minus 1, yi minus 1. And we're given with 3 points, 1, 1, 1, 0, and 3, 2. So let's have a look at this. This is the example test case that has been given to us. So firstly, when you read this problem, you think about how to go about this. So the first primary objective that we are going to have to solve, our first sub problem, is deciding how many minimum number of checkpoints that we're going to need. So according to the description of the question that is given to us, we know I'm going to state a claim, and this claim is that I'm going to define a new term, reachability. Reachability is basically the reachability of a point using certain number of moves of one point to the other point. Now I'm going to explain with this example test case. For example, I can say that 1, 0 is reachable to 3, 2, and vice versa. This is an equivalence relationship. So why can I say this? How can I say this? So I can see that if I start with 3, 2 point and I apply my given move once towards the downside, I will reach this point, which is 2, 1. So basically what I've done is I subtracted 1 from both the ordinate and the abscissa, and that is I've applied the move once and I've shifted it to 2, 1, and then after I reach this point 2, 1, I can apply this move again and reach to 1, 0 by applying this move again and subtracting 1 from both the ordinate and the abscissa. So we know that point 3, 2 and 1, 0 are reachable to one another. I can do this, or I can push 1, 0 to 3, 2 by adding plus 1 and plus 1 2 times and applying this move 2 times. So my claim is that for all reachable points, for all points that are reachable to each other, I have to use only one checkpoint. Why do I say this? Because it's clear from this example set that if I use 2 checkpoints for these 2 points only, 3, 2 and 1, 0, I'll be wasting my checkpoints. because if I selected one checkpoint here and one checkpoint here, then I'll be wasting my checkpoints because I don't need to select this checkpoint. Because if I select 1 comma 0 as a checkpoint, I can push 3 comma 2 into 1 comma 0 by applying my moves twice. So my objective of minimizing the number of checkpoints is not accomplished. So by hit and try, let's try to solve this case first. If I select one checkpoint here, and if I select the second checkpoint here, so we have two minimum number of checkpoints as 2 checkpoints. And let's see how many number of moves do I have to do in order for me to send all of these points into this decided number of checkpoints. And I have to apply this. So 1 comma 1 already belongs to a checkpoint, 1 comma 0 already belongs to another checkpoint. Now 3 comma 2 is the only point which doesn't belong to any checkpoint, so I'm gonna have to apply moves on 3 comma 2, and I apply this move twice. I subtract 1 comma 1 and we reach 2 comma 1, and then once again I apply this move and we reach 1 comma 0, which is the position of a checkpoint, and therefore the amount of moves that I have to do is 2 moves. So let's check whether we got it right or not. Yes, the example output is 2 comma 2. I hope the question is clear with this example test case. So let's expand upon how we're gonna define the term reachability and how are we gonna decide whether one point is reachable to one another or not. So let's take a look upon this move. Firstly, in order to solve this question, we have to see what kind of move this is. So I'm gonna call this move as a diagonal move. Why is that? Because the diagonal doesn't change after I do this move. And how can I say that the diagonal doesn't change? Why am I calling this a diagonal move? We can clearly see from this example that 3 comma 2 is after I apply this move like multiple times, this remains on the same diagonal. But why is that the case? Let's have a look at that. So we define a diagonal move as, suppose this is a grid and this is the x-axis and this is the y-axis, and we're given a chessboard. Let's suppose this is a chessboard. So we're currently starting at here. This is our starting point. So and let's do this move with c equal to 1 and let's move up. So we move here. S comes here. So what we did basically is we moved from the ordinate, we moved to +1, and from the abscissa we also moved +1. So basically the difference between the x-axis x value and the y value initially was y minus xi, firstly when the point was xi comma yi. After I have done this move several times, the final point that I am in is xi plus kc comma yi plus kc. In this case xi plus 1 comma yi plus 1, where k is an integer, k belongs to an integer. And yeah, so the difference before was y minus xi between the abscissa and the ordinate, and afterwards the difference is y plus kc minus xi minus kc, which is kc gets cancelled out, which is y minus xi again. So the difference doesn't change, and through this example, grid example, we're going to see why the difference doesn't change. It's because after this s goes here, the difference, both the ordinate and the abscissa climbed 1 1, and because the ordinate and the abscissa climbed 1 1, the difference remains the same. So initially the point was 1 comma 0, then +1 and +1, then it reached 2 comma 1. And because of the nature of this move, it always remains in the same diagonal. So if I apply this move again, it's gonna move here. So this diagonal is gonna look like this, and I mean it extends both ways. I can also do it downwards, drag it downwards too. If we're starting on this diagonal, then we're gonna stay on this diagonal. So we know, we have explained, we have figured out the term reachability in terms of diagonal. It's not the only thing that is affecting reachability, but it's one of the things that it's affecting. So because the nature of these moves is such that the diagonal doesn't change, we can explicitly say that the minimum number of checkpoints that we need is at least the number of diagonals. Okay, so my claim is that because I've coined this term reachability and I've shown that 2 points, if I call 2 points as reachable to one another, they must lie on the same diagonal because of the nature of moves that I'm allowed to do. And because of the nature of moves that I'm allowed to do, I'm always staying on the same diagonal. That's why the minimum number of checkpoints that I'm gonna need is at least equal to the minimum number of diagonals that is present. I'm not saying that it's the answer, but it is at least the number of diagonals. Okay, so what else affects reachability apart from being on the same diagonal? Let's have a look at that. So let's take an example case over here with c given equal to 2. Okay, so this is the x-axis. This is the, let's only talk about the x coordinate of one diagonal. So I'm only looking at points. I've now segregated the n points into diagonals. So if we were given with n points, I have firstly calculated the number of diagonals. So in this case, we have 5 diagonals. These n points lied on the 5 diagonals, and yeah, so we need at least 5 checkpoints because a move can't change a diagonal. A move always stays on the same diagonal. So that's why we need at least 5 checkpoints in this case. So we need at least the minimum number of diagonals that is present. And how are we going to calculate the number of diagonals that are present? We're going to calculate the various distinct xy minus xi values. This is going to give us the number of diagonals these endpoints are present on. Okay. So after we segregated these endpoints on the basis of which diagonal they lie in, let us flatten this diagonal out. We're going to only see this x coordinate of each point. We can also see y coordinate as well, and I'm going to tell why it doesn't matter. So let's start with point 0 where x is 0, and okay, so let's start off at this point, and c is given to us as 2, so we can move to 2 this point, or I can apply this move over here and I can reach minus 2 point, and vice and respectively it can go over here. If I started off at minus 1, I could go at 1, I could go at 3, I could go at minus 3. So you see, one observation that I do is that the parity doesn't change. After I do this move, the parity doesn't change. Now what do I mean by parity? In this case, when c is equal to 2, it's easy to define parity, right? It's easy to define parity in terms of whether it is odd or even. But if c is not equal to 2, if c is some other number, then how do you define parity? Well, this is one observation that we made. So if you encounter this question in a contest, the observation that you make is that the parity doesn't change when c equal to 2. Okay, so what do I learn from this? Where do I go from now on? So you can see that the parity is almost every time related to the modulus, and modulus c. I mean, c is given to us, right? So my another claim is that not only does in a move, like if I apply n number of moves to a point, not only does it stay on the same diagonal, but also its parity remains the same. That is, its modulus c also remains the same. And how? We're going to see that. So if the x-axis was xi and now it's xi plus kc, where k is an integer. So initial mod c for the x for the ordinate was xi mod c, and final mod c was xi plus kc mod c xi, which is equal to xi mod c plus 0. Here's kc mod c 0. So this is equal to 0. So the parity also doesn't change. The modulus values with respect to c of the ordinate doesn't change, and we have just investigated for x here. You could replace x with y without any problem, and you can see why that wouldn't make any change, right? So we've decided that we're gonna need at least the minimum number of diagonals that are present of these endpoints, but also we're gonna need the amount of different parities that exist, the amount of points lying on the same diagonal, we're going to need the number of different distinct modulus values that is present on those diagonals. So finally combining these two, now I think we've summarized what reachability is and how can we call 2 points reachable to one another or not. So let us summarize this in order to calculate how many checkpoints do we need. So we have to, we're gonna perform two steps. Firstly, calculate the number of diagonals. We're gonna calculate the number of diagonals by calculating the various distinct yi minus xi values. And when we've segregated these endpoints into their respective diagonals, then we're gonna investigate each diagonal separately. Of all the points lying on the same diagonal, calculate the distinct xi mod c values. And when I do this, I'm gonna have my minimum number of checkpoints, because all the points that lie on the same diagonal and have the same modulus c values, they are reachable to one another. And because they are reachable to one another, it doesn't make sense to waste two checkpoints for these 2 points if they're reachable to one another, as we have claimed before, because we can make do with 1 point. We can just select any 1 point of both of them. If there are 2 points lying on the same diagonal with same modulus values as well, then we can just select one value and then as checkpoint and then send the other point to that. For example, if in this case these 2 points might be reachable to one another, so this point and this point, I'll only use one checkpoint. I can place this checkpoint here. We're going to talk about the placement of the checkpoints as that the moves are minimized right now, but right now we're solving just this sub problem of deciding the minimum number of checkpoints that we're going to need. So we can select one checkpoint over here, and because these 2 points are reachable to one another, because I've made it so this point, because they lie on the same diagonal and the values of mod c's are same, so they're reachable. So when if I select only one as checkpoint, then I can send this point to in here by applying some amount of moves. Okay, so these points are not reachable. They have different c values. Okay, because of this, I'm going to need 3 checkpoints. Even though these points lie on the same diagonal, but because they have distinct modulus values with respect to c. And when I talk about distinct modulus values, I am only talking about one of their ordinates, the x ordinate or the y ordinate. For solving this question, I have specifically used the x coordinate, but you can choose the y coordinate as well. It really doesn't make any difference. So, and in this diagonal, since this is the only point that is present in this diagonal, I'm going to need one checkpoint here too. So the total number of checkpoints that I need is 5 for points on 3 diagonals. Because these 3 had different modulus values, these 2 had same modulus values and lied on the same diagonal, so 1 checkpoint and 1 checkpoint here, because there is no other point, and this point lies on different diagonals from all the respective other points. So we have calculated the minimum number of checkpoints that we're going to need. So how are we going to decide what is the minimum number of moves that we're going to have to do? And so basically the way that we minimize moves is we want to place these checkpoints. Where should we place these checkpoints such that the moves that I have to do in order to send all the points into checkpoints is minimized? So firstly, before solving this problem, let us solve a sub problem. Okay, so we're going to solve a sub problem first, and sub problem is minimum travel distance. Okay, so the problem is given as follows. You're given an array A. In this case, array A is 0, 2, 4, 6. Okay? Now, we're gonna have to minimize the value of absolute of ai minus x. So, we have to select an x such that the summation of I equal to 1 to n, the amount of points, n is 4 in this case. So the summation of I equal to 1 to n, the absolute values of ai minus x is minimized. Okay, so this seems rather strange, or you might be wondering why are we solving this sub problem instead, and I'm going to come back to later why this problem is related. why this sub-problem is actually a problem that we're going to solve through by, we have to solve in order to figure out the placement of these checkpoints. So let us look at this as there is a concrete proof of how to solve this problem, and the answer to this problem is that the x is the median. X is the median of array A. So there is a concrete mathematical proof of why x is the median of array A, but it's quite mathematical, and I'm gonna show you a very nice intuitive way for you to see why this is the case, why x is the median of array A. Okay, so firstly I want you to visualize this value, absolute of ai minus x, summation of absolute of ai minus x. I want you to visualize this value as, suppose I choose 0 as my x point. So 2 travels some distance to 0. So I want to see that absolute of 0 minus 0 is 0, absolute of 2 minus 0 is 2, absolute of 4 minus 0 is 4, absolute of 6 minus 0 is 6. So we basically, what I've done is, I am viewing this value, summation of absolute of ai minus x, as I've placed the people, the first person is at 0, the second person is at 2, third person is 4, fourth person is 6. So I've selected 4 people and placed them on these points, and if I select one point as x, in this case my x, let's call x1 equal to 0. If I place this x1 point at 0, then this value, the absolute of summation of absolute of ai minus x, can be thought of as the sum of the distances that all of these people on their respective points will travel till coming to x. So when you visualize it like that, then 2 has to travel 2 distance, 4 has to travel 4 distance, 6 has to travel 6 distance. So let us call this value a. A is equal to summation of absolute of ai minus 0. Okay. Now let us choose a point here, epsilon distance towards here, this point. Okay, so let us calculate the answer in terms of this. So how much distance is every point gonna have to travel to reach this point, x dash? If I want to talk about the summation of absolute of ai minus x dash, which is at epsilon distance towards the left of 0. So let us visualize each point individually. 0 was traveling to 0 with 0 distance. Now it has to travel epsilon distance more. Okay. 2 was traveling 2 distance to reach to 0. Now it has to travel epsilon distance more. Similarly, 4 has to travel epsilon distance more, 6 has to travel epsilon distance more. So this value would be nothing but a plus 4 epsilon, because there are 4 points and each point has to travel in epsilon distance more than they had to when they were reaching 0. Now similarly, let's draw an x2, epsilon distance towards the right of 0. Now if I calculate the summation of absolute value of ai minus x2, then let us again check each point individually. 0 had to travel 0 distance in order to reach 0, but now it has to travel epsilon distance more towards the right. So we were calculating the distances with respect to 0. So a plus epsilon. Now let's talk about 2. Second point had to travel 2 distance to reach to 0, but now it has to stop epsilon distance before. So it is traveling epsilon distance left. Similarly, 4 also had to travel 4 distance to reach 0, but now it has to travel epsilon distance less. Similarly, 6 has to travel epsilon distance less too. So it's minus epsilon, so which gives us a minus 2 epsilon. So as you see that as we go towards the left of 0, the distance that we have to travel is increasing, but as we go towards the right of 0, the distance that we have to travel is decreasing, and this value will keep on decreasing until we reach the median, in this case 2 and 4, because the number of points is even. So This is a nice intuitive way for you to see why in this case to solve this sub problem, x is the answer of x, the value such that the summation of the absolute value of ai minus x is minimized. X is the median of array A. So we get a nice intuitive way for us to see why this is the case. Now, why do I say that this problem is important? Because this is exactly the same problem that we're calculating. Instead, we're not calculating this problem. We define number of moves. So, for example, if 2 points are reachable to one another and I've selected only 1 point as a checkpoint, so these endpoints exist. So, wait a second. Let me draw a picture for it to be more clear. Okay. So the sub-problem that we're solving is basically if I'm given a line and these points lie on the same, this is a diagonal that I've flattened out, and there are these 4 points which are reachable to one another, and each point is at a distance of c from one another because they have the same modulus values because they're reachable to one another, right? So where should I place the checkpoint such that the moves is minimized? And we've already calculated this answer, and this is this point, the median point, the middle point. And the number of moves that I have to do to send this point to this point is, suppose this all of this information, all of these points is x coordinates are ai's, then the answer is the summation of absolute values of ai minus x by c. And we don't have to worry about dealing with fractional values when dividing by c, because since ai and x have the same modulo c, ai minus x will always be divisible by c, because x is chosen as the median point of all of these points. Okay, so we defined reachability in terms of lying on the same diagonal, and make sure that to understand that all of these points lie on the same diagonal and have the same modulus values. That is why they're all reachable to one another. That is why I am sure that the distances between them, I mean in this case it's c, but in an arbitrary case it is a multiple of c, some multiple of c. In this case I've made it as c, but in other cases it can be a multiple of c, but it's always a multiple of c. And that's why I'm sure that we won't encounter any fractional values, because ai mod c is the same as x mod c, because x is some value of ai, and for all values of ai mod c they're equal. So the answer is always divisible by c. So this is going to be the number of moves that I have to do for one set of reachable points to one another. So now we have a clear picture of how we're going to calculate the answer. So let's summarize. Let's summarize the complete solution. So the complete solution is such that firstly calculate the number of distinct diagonals. Check. We've already talked about how we're going to do this. For coding this, you can use an unordered map of a long and a vector of a pair for us to store the points lying on the same diagonal. So we segregate the points lying on the same diagonal, and after we've segregated these n points into some diagonals, we calculate for each diagonal separately. Of all the points lying on the same diagonal, we calculate the distinct unreachable points. So basically, how do we calculate the distinct unreachable points? We calculate the distinct mod c values of points lying on the same diagonal, and this will give us the distinct unreachable points, and summing these two up, we're gonna have our checkpoints. We're gonna have a minimum number of checkpoints. So after we figure out the number of checkpoints, we are gonna have to figure out where to place these checkpoints. So of all the reachable points, choose position of the checkpoint as the median of these reachable points. All of these points are reachable. For one set of reachable points, select the median of those points and reachable checkpoints, and place that checkpoint over at that point. Then after you've placed that checkpoint on that median, then calculate the minimum required number of moves. Okay, and this is how you solve this problem. So we're gonna go over the code once so that you get a understanding of how this works. So I'm gonna explain how this code works. Okay, so I've used some macros, but so yeah. Firstly, we take the number of test cases. Then I start a loop for each test case. I make two values n and c. Input these two values, and then I make an unordered map. This is basically a hash map if you're using some other language. The hash map if you're using Java, of a long long. LL stands for long long. I highly recommend that you use this macro, because for every other question you're gonna need a long long, and long long is just too big to type. So LL is a long long. Use this macro if possible. So I've made a hash map of LL and a vector of pair LL comma LL, and then I input n points. I make 2 points x comma y. Then I segregate those points on the basis of which diagonal they lie. So I have calculated this y minus x values, and I store all of these points on the same line on the same diagonal with the same hash map value. Okay, so after I've done this, I iterate over all of the diagonals. This is an unordered map which segregates all of the points into various diagonals, and of all the points lying on the same diagonal, I select the number of points. This nn will select. Nn is the integer, and it is the amount of points that is present that lie on the same diagonal. And I create another vector vec, and of all the points lying on the same diagonal, I push it into y dot. I push the x value, the ordinate. Y dot first is the ordinate, and y dot second is the abscissa of points lying on the same diagonal. I push the ordinate into this vector vec. So after this, I make another unordered map of an LL and a vector, and for all of these points lying on the same diagonal, I now segregate these points on the basis of their modulus values with c's. Now to keep in mind that I have used vec of I %c plus c %c. This is something that you have to do for you to not encounter any negative modulus values, because C++ works in a very strange way. Because a modulus values, if that value is negative, if vec of I can be negative, because it's just the x coordinate of some point, right? So it can be negative, and sometimes the modulus of a negative value can also be negative. So that's why a plus c and %c. So I've literally made sure that all of these modulus values lie strictly from 0 to c minus 1, and I have pushed back all of the values that are same, that have the same modulus, all of the x coordinates that have the same modulus values with c's, and I've saved them in an unordered map, U map. So now I iterate over all the elements of a U map, auto and y of U map, and now all of these points that I encounter, they are now reachable. All the points having the same modulus values and the same diagonal, recall that we term them as reachable. So all of these points are reachable, and for each and every point that we do, we increase this CC. CC value shows the number of checkpoints that we use. So for every set of reachable points, we increase this value. So the number of checkpoints is the number of distinct unreachable points, set of unreachable points, and this is iterated and gets increased every time we encounter certain points with different modulus lying on the same diagonal or lying on different diagonals altogether. So we sort these values which are reachable to one another, then we select the size of how many points there are, and then we know that the median, since we sorted this, we know that the median will lie on n by 2. So we select the O denotes the number of moves that we have to do. Then we calculate this as O plus equal to absolute of y dot second I. So y dot second I basically denotes the x coordinate for all of the reachable points, minus y dot second of the median of all of these points by c, And we talked about why this value won't ever be fractional, because all of the moduluses values are same between n by 2 and I. So, and we add this value towards O, which is the number of moves, and we just output the number of checkpoints and the number of moves. So yeah, this was the question, guys, and I hope you understand everything that we went through. And yeah, this was not a very tough problem, but this was a combination of very good, very easy problems. And yeah, so hope to see you next time. Thank you.